Thank you so much for the great introduction. Thank you. So, hi, everyone. Today I will be talking about something that is slightly different because all of the previous speakers, talked about, the blockchain itself, right? The different applications of the blockchain. Like Alex said, I'm coming to this ecosystem from slightly different vantage point. Basically, I've been in sort of enterprise computing for all of my life, helped with some of the database systems. But I think maybe a few years ago, we started noticing something that was pretty unusual, and I think I'm going to share it with you, and hopefully I can maybe impart some of the excitement that we see in this next wave of computing. So with that, let me actually give you this obligatory slide. How many of you have seen this slide before, or something similar to it? OK, 1, 2, 3. OK, so let me at least very quickly go through it, right? This is this typical positioning of different industrial revolutions that has happened throughout human history. And what's interesting is everybody's agreeing that right now we're at the phase of the fourth industrial revolution. And the key thing that makes it different from the previous one, which is basically sort of the electronics and computers and automation, is that all of a sudden we're connecting cyber and physical. So cyber-physical systems finally become reality. And I would venture to say that when you say cyber-physical, physical is the new aspect to it, right? Because we've been doing cyber for quite some time. If you think about it, though, our whole industry is basically this constant movement between different phases of how we think about computing, right? And this pendulum has been swinging ever since, I guess, 50s, maybe even before that. Just a few milestones that we all can recognize, because I don't think any of us is old enough to actually remember the mainframes. Maybe some are. But we definitely can recognize the 80s, right? 80s was a period when the enterprise computing appeared. Microsoft Windows was the sort of epitome of a personal computing, right? Everything was actually, if you think about it, sort of decentralized because people had computers on their desktops. They started digitizing their business. They moved from paper to digital. And then all of a sudden, cloud computing happened, right? So all of the same power started being concentrated in the data center. Most of the applications were delivered as software as a service. We now have this enormous concentration of power between Google, Amazon, Microsoft, some of the smaller cloud players. And it feels like it's impossible to do anything that would radically challenge that. But I actually submit to you that yet another set of computing is actually already here. We just don't notice it. In fact, there was a Gartner report a few years ago that calculated that the amount of compute power available outside of a data center started to dwarf the amount of compute power available inside of the data center. And think about it for a moment. Again, all of these giants of the industry concentrating power in their data centers, and yet that is in nowhere close to the amount of computing that's available just all around us. And I'm talking about things that are here in the city, right? Things that are attached to the light poles, things that are attached to the traffic lights, small computers helping automate the factory, chemical plants, stuff like that. So we call it the edge computing. Some people used to call it IoT. I don't like the term IoT because somehow it invokes the consumer aspect of it. So I like the industrial aspect of it much more. So let's call it edge computing. And let's agree that what it means is it has to be ubiquitous, it has to be real time, and it has to be cyber-physical. So all of these compute devices actually have to be attached to something that can either change the real world or get inputs from the real world. And if you assume this viewpoint, then it's actually very easy to understand why the model that we all are used to in the cloud computing space will not actually work out for us anymore. So the model so far has been that even for the IoT, even for the smart connected devices, the best thing that we can do is just get the data points and send them to the cloud as quickly as possible. Because remember, all of the real compute is actually still happening in the cloud. So what we're proposing is what I would like to introduce to you, is that I think starting basically from about now, a lot of the same computation will actually start happening at the edge itself, right? So the day of tomorrow will be, yes, there will still be some data points, going back to the cloud, but you will see a lot of autonomous behavior, happening on the edge itself. Because, at the end of the day, the real world is autonomous, right? You don't want your smart light to not operate, because your smart switch actually has to send data through the Amazon cloud, and only then your smart light can actually switch on and off. So if you assume that this is what's going to happen, then the real question that you will be asking is like, well, but does the technology that would actually allow us to do this type of autonomous behavior exist today? And the good news is that we actually have bits and pieces of that technology. So on one hand, I mean, today, we do have all of that compute operating somehow, right? This is known as domain-os embedded computing. And embedded computing started as a really tiny devices, with real-time operating systems, highly specialized software development cycles, pretty much very difficult to impossible to upgrade or update. So that exists today. On the other hand, we actually have the cloud computing, which we all know and love today. And this is the software development cycle that makes us so productive as developers. Because we no longer even have to think about servers, right? We think about virtual machines, we think about Docker containers. Sometimes we don't even think about those, because we think about Lambda, service as a function, and all we focus on is our business logic, right? The rest of the concerns are being taken care of by the infrastructure itself. So what if we actually try to take the best of both worlds, take the embedded, sort of close to the real world, viewpoint, and mesh it with the kind of application development strategies that we've developed for the cloud? That I would call a cloud-native edge. And that's, in fact, what sort of the company that I'm now associated with is trying to do. So the mission of the company, the vision for the company, is to create a new edge economy that allows application to run anywhere. So that's a pretty bold statement, but the mission is maybe even bigger. We would like to be the largest compute company on Earth without owning any infrastructure, the same way that Uber is the largest taxi company on Earth without owning any taxis. So I will tell you a little bit about what we're building, because I think it's actually very relevant to how blockchain sort of factors into this conversation. So the stack that we're building basically starts with the hardware. So we're not a hardware company, we're a software company. But we start with essentially hardware that is capable of things that can guarantee trust, because we want our objective reality to be trustworthy. And Gene actually gave a really good point when he was talking about this vault, and he was talking about your driving DNA. So it is absolutely important for us to have the vault that can actually store that information. But ask yourself, how does that information get into the vault to begin with? How can you make that information trustworthy? How can you make sure that whatever is plugged into your car is actually being really plugged into your car and being driven, throughout your neighborhood, as opposed to you actually giving it to your really careful buddy, so that he or she improves your driving records, right? You need to have that trust with reality, and the only way to make that trust happen, as we all learned, through the blockchain exercise, is to actually make it computationally based. But in order for it to be computationally based, you actually have to have hardware that is essentially capable of providing you some of the cryptographic guarantees that you cannot really easily tamper with. So we start with the hardware layer. Then on that layer, we basically provide essentially a layer of virtualization. So we're virtualizing the hardware so that we can then build a layer of the platform itself. And that would be very similar to, let's say, what Amazon or Google are running in their data centers to essentially enable all of the virtual machine management and Docker management and all of this other stuff. There's basically an operating system that's running on the hardware itself. And we're kind of building the same. So you could compare us, very roughly, because it's definitely not the same to, let's say, CoreOS. But the biggest difference between us and CoreOS is the physicality. Remember, I told you that the proverbial fourth industrial revolution is all about cyber physical. So far, all of the technologies like CoreOS have been developed in the understanding that they will actually run in a data center. Data center is not a physical, physically specific environment. In fact, data center is full of commodity computing as far as I can tell, because every single server in that rack is about the same. The network doesn't really change. The physical security is guaranteed by a guy, with a machine gun in front of the data center. It's a very different environment compared to the real world, let's say, of a city like Amsterdam, where these computers are basically, first of all, they're everywhere. Second of all, they're available to essentially physical attacks by people just walking to them with USB sticks or just trying to steal them. And third of all, I mean, the networking infrastructure that connects them together changes all the time, because it may be connected to the Ethernet today and to some kind of a Zigbee or radio technology tomorrow. So that changes all the time. So designing this operating system layer with the physical sort of guarantees, with the physical understanding in mind, is very important to us. And then, of course, on that layer, you have the apps in the very same sense that you would have them in a cloud computing environment. The apps can migrate. And just very quickly to finish this off, we are targeting all of the compute devices that you can possibly think of in this cyber-physical space. So we can run on a board that is $7 based on ARM, all the way to a real server. And we kind of give you the platform, right? So the platform basically provides you with security, management, networking. And a lot of that, today is done by various vendors in this space. We're just connecting it all together. So the platform is there for you to use, to utilize. But are we done? Are we really done? Well, even if we give you that platform, I think the question then remains, how can these applications communicate with each other? And one way to answer it is, well, the same way that applications have communicated with each other for ages, which is, using TCP/IP and, doing maybe HTTP requests. And that's one way of doing it. That's sort of the distributed side of it. But we also feel that it would be extremely important for these applications to essentially communicate without knowing the other party. Right? Because again, we're trying to build this trustworthy environment, and in a trustworthy environment, you actually knowing who the party is with whom you're communicating is not necessarily a good property of the system. A lot of times, you need that communication to be anonymous between essentially the providers and consumers of a certain service without disclosing the identity of those providers and consumers. So the edge trust model is absolutely different. And on the edge, you essentially have these applications connecting the three parties, right? So first of all, there are obviously developers. These are guys like myself, gals like you in the audience, who are just developing software for these systems, right? But there's also essentially on the edge asset owners. These are the people who have pretty enormous investments in the physical infrastructure. So an asset owner, for example, could be a telco company, right? Telcos are going to roll out 5G pretty quickly, and that will be an enormous expenditure of capital on their part. And they will be stuck with these assets for years and years to come. So obviously, they would like to be able to monetize those assets as much as they possibly can. And in order for them to do so, they actually have to make sure that those assets can not only do what they're meant to do, which is basically route your phone calls, but also do some of the additional functions. And that's why they need access to developers. But third of all, you actually have businesses that are essentially trying to connect the two and make sure that you can innovate using the assets that the asset owner brings to the table, the code that the developer brings to the table, but then the businesses are taking risk on essentially delivering the next generation applications that can actually make money. And how the money changes hands in this ecosystem is actually very important. So we feel that this ecosystem needs to be an edge market economy. And as a quick aside, I would actually, anybody who is doing crypto or blockchain, I would highly recommend reading this book that on the surface has nothing to do with any of that. It's called Debt, The First 5,000 Years. It's actually written by a really good guy who is not an economist. He's actually an anthropologist. The insight you will get from it about what trust really is are just tremendous. So read the book. Now, obviously, in order to manage that trust, we're using blockchain. That's pretty easy to understand. I think the blockchain is to decentralize what internet was to connect it. Remember, the applications used to just talk to each other on the internet. And that was the big revolution that gave us sort of the previous industrial phase. Right now, we're doing decentralized. So again, the blockchain is the same communication medium for the next generation types of applications. By the way, again, as a quick aside, people ask me, well, is it really that new? And it's kind of not really that new. I mean, you can kind of sort of have the same concepts with even relational databases if you really squint. But I think, some of the cryptographic properties that are being built into the blockchains are making all the difference. And of course, the nice thing about blockchains is that there's so many to choose from. So I will very quickly run through this section because not enough time, but just give you a couple of pointers. So obviously, there's the usual suspects. Then there's Hyperledger, which Chris talked about quite nicely. But we actually found something that caught our eye specifically for the kind of applications that we envision to be running on the edge, and that's EOS. So EOS was really interesting to us. And I highly recommend you guys check it out, because it's one of the first blockchains that really took it to the next level without really trying to be just a specific blockchain for one particular use case. So what makes it interesting to us, by the way, is not mainnet. So these people are now trying to run mainnet. That's fine. There's all sorts of issues with governance and whatnot. We're actually interested in the code, not necessarily the mainnet, because we feel that our customers will be actually running the networks themselves, not necessarily participating in the mainnet. So what's cool about EOS? So first of all, the free usage, meaning that you actually, as an originator of the transaction, you're not supposed to pay like any gas, like you do today in Ethereum. So that's free. The system takes care of, managing the compute power, in other ways. Low latency, it's pretty nicely done, again, for the kind of edge applications that we have in mind. It also has basically the ability to essentially communicate between the different sides of the blockchain. So you can kind of have, built right into the protocol this idea of, having a public blockchain and a whole bunch of private blockchains, right? And those will be communicating with each other. But what's also very interesting to us is this focus that they have on essentially secure execution of code. And that's really what made me a believer in EOS, because when I read their positioning statement, it was clear to me that they were positioning themselves as an operating system rather than a blockchain, right? Because if you read it, I mean, this is something that would be applicable to like a general purpose distributed operating system. There is not really anything blockchain-y or cryptocurrency or anything like that about it, right? And that's what we're trying to leverage. Now, the secret sauce behind EOS is obviously a delegated proof of stake. That's what makes all of the properties that were interesting to me possible. I will not get into the details, but check it out. It's basically based on this idea that you have only a select group of block producers, 21 to be specific, that are validating all the blocks. But how those 21 get selected, so you don't have a centralized system, that's actually the secret sauce that makes the whole thing go pretty well. So with EOS, do we have enough to build what we're trying to build? No. There's still missing bits and pieces, and that's what I'm actually working on with the team in my company. There's also other teams working on it. If any of this is interesting to you, I guarantee that I will not be able to explain all of it, but I need to give you just enough of pointers so you can catch me after the presentation and talk to me about any of this. So whirlwind tour of what we're building, what we're investing in. So first of all, we need to build the decentralized identifiers and make it reliable and robust. So we are leveraging a lot of research that's done out of the Hyperledger Foundation, Indy, but we're applying it to EOS and trying to figure out how the two can go together. So with decentralized identifiers, we need to, again, ensure those properties that the two participants in a transaction will disclose as little about each other as possible. So, and again, one of the keynotes, there was a really good example of how you can, buy a pack of cigarettes without really disclosing your age. That's exactly what I'm talking about. And, there's ways of doing it. Again, this is a slide taken out of the Indy presentation, so I think they're doing pretty well. We're also investing in secure enclave-based code execution, because again, if we're running arbitrary code, because again, EOS to us is a distributed operating system, right? So we're no longer talking about smart contracts. We're talking about literally running, arbitrary code in the system. So in order to do that, you have to do two things. You have to protect the code from the operating system, but you also have to protect the operating system from the code. The second one is much easier, because that's what's been happening in the data center for essentially at least 10, 15 years by now. The fact that in a public cloud, Coca-Cola and Pepsi can run on the same computer given to them by Amazon is a testament that you can actually protect applications from each other, and you can protect the host operating system from the application. The reverse is actually much more difficult. How do you protect the application from a malicious operating system? So we are trying to solve it, based on the CPU capabilities. And there is amazing work done by the Graphene SGX team, and also Joanna Rutkowska from Project Golem. That's actually, a picture taken from her slide. There's still major challenges remaining, and these are actually hardware challenges, because what we're doing here, we're trying to use Intel CPUs to essentially give us the first chain of trust. So the CPU itself is now cryptographically signed. Think of it this way. And from that root of trust, we're trying to bootstrap the rest of the system, but it's actually very difficult to do it in small steps. And Intel is doing an absolutely right, set of they're doing actually the right job in essentially sort of disclosing it very progressively, but I think we need to push on them to make it a little bit more open and a little bit more reliable. And if we do all of that, then what will happen is we will actually be able to build the holy grail of cyber-physical systems, which is oracles. Oracles are something that connect cyber and physical. These are basically the systems that essentially inject physical properties of the real world into this blockchain that we're all operating on. Because the blockchain itself is completely basically virtual, right? There's absolutely nothing physical about it. So if it needs to know the driving speed of your car, because that's the part of the DNA that Gene was talking about, your driving DNA, that information has to come from an oracle. So that's what oracles are. There's also a subset of oracles. Some people call them, from time to time, hardware epithets. So the Ledger company that's actually doing cryptographic hardware wallet is, calling them this way. So the two terms can be used interchangeably. What we're trying to do at Zedata, we're trying to actually get away from dedicated hardware. That's what Ledger is building, to basically give you the capability of essentially running oracles on absolutely any kind of an edge system. So that's what we're really trying to build. And with that, I apparently ran out of time. But I would like to leave you with this quote. If there's anything that's a breakthrough, next generation set of things that are going to happen in the blockchain space, I think that's basically the oracles. So keep an eye on oracles, keep an eye on hardware epithets, because I think that will be the last missing link between really building this truly cyber-physical system that will connect the reality with the virtual world. Thank you so much.